Well, good morning, everyone. I am Mary Turner, Director of Training here at BRO, and I would like to thank you all for attending our session this morning where we're going to talk about the microstructure feature within ASAP, which is a process that we've inserted into the software over the past couple of releases and enhancing it as we go along to allow simulation of very complex structures on surfaces, typically for scattering, diffusing type applications. As I mentioned, I am Mary Turner. We also have some other people from BRO who are listening in. If you have questions, please, you can obviously email them to us at any time. But during this session, if there's some particular question related to it, you all have access to that little chat box, and please use it, and someone from BRO will try to answer your questions as soon as we can get to them. Let's start on talking about microstructure, how microstructure is applied, and exactly what we mean when we're talking about microstructure. But where I want to start is with a little bit of history. I noticed from looking at the list of attendees, and I would like to make a special thanks to those who attempted to attend last week, and we had technical difficulties. Today is another rainy day in Tucson, so 2 Wednesdays in a row, but things look to be going a whole lot smoother today, so I do appreciate you coming back. But a little history about how you have performed these simulations in ASAP in the past, because most of you are somewhat familiar with ASAP. I'm familiar with most of your names. Typically what we've done when we've modeled texture on a surface, for instance, for any type of illumination applications, architectural, automotive, even LCD type simulations, what we've done is used what's called the scatter function. And again, since most of you are familiar with ASAP, if you see something in capital letters, it's sort of indicating it's an ASAP command. And basically what's been done historically is a reference sample typically has been acquired in some fashion. So something that's been made to the manufacturing standard that will be applied in actual production. And that sample, that reference piece, is put inside some type of goniometer, and measurements are made. So light is sent incident on that sample, and then a detector captures the energy as a function of angle. And as you use different angles of incidence, of course, you'll have different amounts of energy scattered into the different angles. Typically, what you do is at least measure within a plane a total angular range of 180 degrees, if it's at normal incidence, plus and minus 90 relative to the specular. If it's at some other angle of incidence, lesser angles in the forward direction, more angles in the reverse direction. There are also some goniometric devices that will actually measure the scatter into a complete hemisphere. So you can model over the full hemisphere as well as get information about total integrated scatter. And then after the measurements are made, this is converted into some form of parametric model. For instance, in ASAP, the Harvey model, the polynomial model, even the user BSDF model. And typically these are relatively useful and very accurate for surfaces that are relatively smooth, and relatively, of course, is a very broad term. Some surfaces that are significantly not smooth can actually still be simulated in these ways. And these models allow for both isotropic as well as anisotropic models. So you can do a lot of reasonable approximations. But the problem is, as we move forward in automotive technology, architectural technology, as LEDs become a much more dominant source of our lighting, we need to have much more complex structures for our scatter, to introduce the scatter or diffusion. And these complex structures are not really well represented or at all by a simple measurement. Scatter is highly dependent upon angle of incidence. And again, there is a physical structure to some of these diffusers that are totally lost within a simple measurement. So we have to do something else. And so when we talk about these structured diffusers, The diffusers today have very highly structured shapes. They may be prismatic type devices that may have anywhere between 5 and 15 separate faces that make up each of those individual prisms, and some of those faces may have AR coatings or roughness or scatter applied to them. Others may not. You also could have a cavity structure that consists of possibly hundreds of separate faces. And then you need to have a lot of those structures positioned over this total surface, maybe hundreds, maybe thousands, maybe even millions. And when it comes time to try to integrate that complex structure into an ASAP simulation, you're going to run into a lot of difficulties and issues, and in a lot of cases, some impossibilities. Even if you had a structure that you could build up as an accurate ASAP model, simulating a large number of those structures is very time consuming because you need to have enough rays to make sure that you sample all of the geometry sufficiently to make sure you have reasonable and accurate statistics. And more importantly, so you go through and you build up this structure that may have hundreds of separate faces or even dozens of separate faces. You put a few thousand of them in your system, and then you decide you need to change it a little bit, or you want to do a tolerance study. What happens if? Attempting to optimize or in any way modify an array of these structures is going to be extremely difficult. You're going to have to just find ways to go in there and keep changing things, and if you're doing it within a CAD environment, go back to your CAD program, bring them back in. If you've changed the number of faces, reapplying all the optical properties, etc. So you can see that there's going to be a great deal of difficulty associated with trying to model something like these types of structures. So what we have come up with, or we think we've come up with, is a much better technique. And this technique needs to take into account several different things. You need to be able to account very accurately for large numbers of these structures. You need to allow for varying size and pitch between the individual elements. You need to allow for a rapid change or update of the system when you make changes to the structure. And probably the most important part or consideration for most of us as engineers is that you need to get accurate simulations in a very reasonable amount of time. And what ASAP has introduced in an attempt to provide you with this capability is a technique that we call microstructure. And of course, it's capitalized, so microstructure is the command as well as the descriptor. So let's talk a little bit about microstructure in ASAP. And what microstructure is fundamentally is a replicated geometrical pattern that will be positioned on a surface with an appropriate distribution so that it alters the light distribution that's incident on that surface. And in this particular case, what we see here is sort of a backlight display issue where we have a series of refractive bumps, microlenses, if you will, placed across the bottom of the light guide, and they're going to redirect the energy that comes through the display to the top of the guide. And obviously the top of the guide is removed from this picture so you can see what's underneath. So that's a very simple example of microstructure. And in this particular case, it's something that could easily be modeled explicitly within ASAP. You could go in and you could create this array of these lens structures, microlenses, if you will. But there are other issues involved, so which we will continue to talk about. And so, double-clicked there. So now once you have those defined, you can apply optical properties. And also, just as a mention on that previous slide, you may have noticed that the size as well as the distribution of these lenslets did vary as we went across the surface. So we can vary the size, we can vary the spacing of each of our microstructure elements as we go across our surfaces. And we will talk about that, and that's a large part of what we're going to talk about over the next several minutes. Now, once you've applied optical properties, for instance, index of refraction, dispersion if you're concerned with, for instance, a white light source, which we are quite frequently, you can apply surface coatings. And if you have multiple faces, you can apply coatings on one face and not another, or different coatings on different faces. You can ask the simulation to take into account Fresnel reflections. You can also choose to use Monte Carlo simulations or not. Typically for illumination, we're going to use Monte Carlo. You can also apply surface texture. So although surface texture, the typical scatter model that we've used historically, may not be appropriate for these structural elements as a whole, individual faces on that, for example, may be roughened and maybe that you may, in a way, you may want to represent as a Harvey or a Lambertian type distribution. So on a face-by-face basis, you can choose to apply a typical scatter model. You can the simulation needs to take into account total internal reflections, polarization, anything that could occur to the rays as they propagate through your system, including the device that has these microstructural elements applied. So the technique that we use is to define what's called a unit cell. Everything starts with the unit cell. And there are a couple of restrictions/limitations, and we will talk about them right here. And these graphics sort of attempt to demonstrate that to you. Basically, the fundamental requirement of the microstructure is, as the word micro implies, it is small. And our unit cell, which represents each structural element within your microstructure as a whole, needs to be small compared to the local surface curvature, so that in the local region around where we're positioning a microstructure element, we can assume that the surface is effectively flat. Okay? And then we can then represent our microstructure as a two-dimensional replication of this unit cell structure. And each of our basic structures need to fit within the unit cell area. Okay? Also, the microstructure needs to be so small that rays intersecting any region on the parent surface can be randomly distributed across the unit cells within that region. And if the ray is coming in at such an angle that it would actually be incident on multiple structures, then that will also be taken into account by the simulation. Okay. The one requirement, or the fundamental requirement, is our structural geometry must fit within a boundary that you define using an edge rectangle in ASAP speak. So you'll start by defining an edge rectangle, and then you will create the structure that makes up each of the individual microstructure components within the bounds of this unit cell. And here's a typical microstructure element. In this particular case, it is a prism and applied to this rectangular edge. So this rectangular edge is going to be assumed to be flat relative to the surface where this edge is positioned. Now, in this case, the microstructure element is this prism, which is much smaller than the rectangle, than the rectangular edge here. So there'll be a spacing effectively between each of the microstructure elements. And in this particular case, it was, for example, made of uncoated glass. But as I mentioned, you could put different AR coatings on different surfaces. You could apply surface scatter or texture to different faces. Any type of optical properties can be applied to any of these component faces. And then put it together. For example, again, the dimensions of the microstructure need to be small compared to the surface on which it's placed, but you're still using ray tracing. So remember, the dimensions must be large relative to the wavelength. And then each of the elements will be positioned within this unit planar cell, whose local axis will vary with the curvature of the surface. So in this particular case, we have this horn shape, just to give you something interesting to look at. And we can see the positioning of these different elements. The positioning of these elements here is simply for visualization purposes. You only define one unit cell. ASAP determines where the rays would hit on the unit cell. There aren't millions of unit cells stored in memory because that defeats the purpose of trying to give you rapid ray tracing. But this basically allows you to see the orientation of the cells across the surface. And you also could simply ask ASAP to display what the local axis is for each of the individual, for the array elements as they would go across the surface. So what does this give you? It gives you a method that's relatively easy, actually extremely easy in a lot of cases, in most cases. It is, more importantly, very, very fast and extremely accurate. You only model a single element, so you don't have to create explicit representations that are extremely hard to model. Maybe you have too many objects. Maybe you want hundreds of thousands of those, and ASAP will not let you do that. It's also very hard to apply the explicit models to arbitrary surfaces. If you have a curved surface, let's just say a spline or curved surface, and you want to apply several of these explicitly, then you're going to have to go in and reshape the interfacing surface at each position to make sure it actually fits to the shape of that structure, so you have a good interface information, no wrong side errors, etc. If you have an explicit representation, it's going to be very difficult to change, because if you need to modify anything about the shape or the size or the positioning, you're going to have to go in and change them all. It's also very difficult to optimize. This is a very, very time consuming if you're trying to change or modify each of these tens of thousands of items each iteration through. And of course, it's very hard to store on your computer. Since you only have a single element, ray tracing is going to be very fast. A comparison of explicit models to the microstructure models, an improvement of 5 to 100 times, and in some instances more, than the ray tracing of the explicit models. And it's also going to be very, very accurate. You're going to be able to apply all of the optical properties of interest: refraction, reflection, TIR, scatter. You can allow for Fresnel reflections. You can set your limitations on ray splitting. You can do Monte Carlo simulations, all between these microstructure cells. So you're going to get a very, very accurate answer very quickly by using this microstructure process. So of course, we must talk about the ASAP 4-step process. So how do we go about setting this up within ASAP? You can use surfaces or edges. The only one requirement is the basic rectangular edge must define the boundaries of the unit cell. Or you can, and typically you will, define your structures within CAD and import a step or an IGES file. You can construct them from any number of objects. We have done simulations that it covered hundreds of thousands of structures, each of which had up to about 1,000 faces with no difficulty at all. You can have any combination of refraction, reflection, scatter, absorption, ray splitting. It supports polarization ray tracing, supports Monte Carlo ray tracing. It also allows you to vary the pitch, the size, and or the spacing of the different elements. So it's very, very capable. And let's take a little look at ASAP speak. So the first you need to do is define the cell boundary, and again, a rectangular edge at z equals 0, and it must be z, and it must be 0. Size is up to you, but this is the initial orientation that your unit cell must have. And now you'll define the geometry. So for these little micro lenslets, we define them using an ellipsoid and bounded them as well. So that's the basic ellipsoids. And then we defined a microstructure. Now, just as to reemphasize, although we're defining this as part of a model, which is the typical scatter definition within ASAP, these are not scatter simulations. These are ray tracing based on the actual microstructure, but just in sort of maintaining the standard hierarchy of ASAP script definitions, this is where we chose to position the microstructure. You can define the axis of orientate, the symmetry axis, and you can define the symmetry axis in global space or local space, and this simply indicates which which objects make up the microstructure. But again, real rays are traced through the real peen geometry, even though it looks like it's a simple model. And then to apply it to a surface, simple standard interface command, and then we apply our scatter model. So far, what we've been looking at is the basic application of the microstructure. We've looked at how we might define structures, how it affects the basic ASAP four-step process in defining your system, doing your ray tracing, and performing an analysis. And that's the general information you need to go about using microstructures as part of your simulations. But of course, what you probably also want to see is how does it work in the real world, if you will. And what I'd like to close with then is just show you a couple of comparisons of models where the microstructure can appropriately be used, but also with systems that we could actually ray trace explicitly. And the first we'll look at is this light guide. And in the explicit model, these individual peens were all defined as separate components in the system. And you'll notice there's a relatively large number, or a moderately large number, and that their positioning and size across the face of the light guide does change. So again, a very realistic model of this type of light guide. And here is the result of the ray trace simulation. In this particular case, we modeled effectively the same structure, but we only defined a single unit cell and used the microstructure approach to effectively create the full geometry. And here is the result of that particular ray trace. And I think you'll agree that for all purposes, practical purposes in an illumination analysis, the results of these two ray traces are identical. The key difference in this particular case is that the unit cell approach traced 5 times faster. So again, exactly the same results, but with a significant saving in time for the ray trace, and also, and probably more importantly, in time necessary to construct the geometric representation initially. And another more complete visualization, this is the case of a bicycle tail lamp. And what we see is a ring pattern of LEDs, and we have our red dome light, if you will. But between the LEDs and the outer red plastic, we have this prismatic structure that acts as a diffuser. Let's take a look at that a little bit more closely. And what we're doing is looking at a rendering of this within ASAP to allow you to see sort of the shape as well as the orientation and positioning of the microstructure across this diffusing dome. And again, we'll talk about results of the ray trace simulation. This model could also have been built up rigorously and completely within ASAP, or we could have used the unit cell approach. And here are the light intensity profiles at the output of those bicycle safety lamps. And again, I think you can agree that we have identical results between the two simulations. However, when we use the explicit model, ray trace time alone was 10 CPU hours. And the unit cell model approach, however, was only 0.3 CPU hours. And again, obviously, the amount of time it requires to create a single model of the prism versus creating all of the individual prismatic structures is also a significant benefit that isn't really accounted for in this particular calculation. So what I'm hoping you can see from this discussion of microstructure is that microstructure allows you to define very, very complex diffusing structures used in illumination applications or other applications to very high accuracy, but with a significant savings in both design time as well as ray tracing time. I'd like to thank you all for tuning in to this webinar. And if you have any questions at all related to the microstructure process within ASAP, we would certainly welcome you to send us an email, ask us questions. If there are other functionalities you would also like to see us talk about, please let us know about those as well. Thank you very much. Goodbye.